Turning our attention back to enolates, these anions alpha or next door to our carbonyl. This is also an equilibrium event, but it's one where this equilibrium lies, towards the enolate or towards the carbonyl form, depends upon the base we're using. Because that's all it is. It's an acid-base reaction. And so in order to determine, is this equilibrium going to lie over here? Is it going to lie over here? Is it going to be significant amounts of both? We need to go back and think about acid-base chemistry again. And in particular, what we need to do is we need to compare the pKa of our two acids. One acid, the acid on this side being the alpha protons. Like I've said, for aldehydes and ketones, that's usually somewhere around 20. When we talk more about esters, which we will later on, it's about 25. Then the other thing we need to think about is what's the pKa of this proton? So we're really comparing that proton and that proton. And here, the pKa depends upon what is the base. What base are we using? So if we're imagining that we're using here as a base something like sodium hydroxide. Well, our conjugate acid of our base then is water. The pKa of water, somewhere around, 14, 15. Let's call it 14, just for right now. And then we need to remember, in acid-base reactions, we want to favor the weaker acid. Now this is one of the things that's easy to get flipped around. Remembering, our weaker acid is actually going to be our larger number. So if we're comparing 20 and 14, although we still don't think of 14 as really an acid, it is comparatively a stronger acid, a significantly stronger acid than here. So remember, equilibrium favors the weaker acid. Weaker acid, larger number. So if we're using sodium hydroxide, this equilibrium is basically entirely this direction. There's hardly any enolate. If we want to get an enolate, we need to use a stronger base. Now we can help that out. We could use, say, something like potassium T-butoxide. Now, the conjugate acid of potassium T-butoxide is T-butanol. And here, the pKa of T-butanol, although it's again an alcohol, is significantly higher. The pKa here is somewhere around 18. Around 18. That means this equilibrium is still definitely this direction, but there's a bit more enolate, still mostly carbonyl. If, as we're going to see for some of the chemistry we'll talk about, we really want this thing over here, we want it to be essentially completely enolate, we need to go to a much stronger base. And here, as I slide this up a little bit to make it easier to draw, our much stronger base that we're going to typically encounter is something called lithium diisopropyl amide. So it's this nitrogen-centered anion. The abbreviation for this is LDA. And the conjugate acid of that is just the amine, diisopropylamine, where we've protonated that nitrogen. pKa here is in the ballpark of about 40. So Now, if we were comparing 20 with 40, well, 20 is the lower number, it's the stronger acid. 40, that's a much higher, much weaker acid. Our equilibrium favors the weaker acid. Now this equilibrium is going to be, boom, there, and such a tiny reverse arrow that you can't even see that. Okay, that's intentional. There's essentially no reverse equilibrium here. It's all enolate, and we're going to use LDA an awful lot coming up. One other thing about LDA, this is not some miracle reagent that comes from nowhere. We actually produce LDA starting from diisopropylamine, and then we treat it with something that's even stronger base. Typically what's used for this is actually N-butyl lithium. So one of those organometallic reagents that we talked about, we know how to form. Hopefully we remember that. Acid-base chemistry, it will remove this proton, generating LDA, and then butane as a completely innocuous byproduct. So, enolates, we can have conditions that give us not much, maybe a little bit, or ones that essentially completely convert our carbonyl form over to the enolate side. It's all about acid-base chemistry favoring the weaker acid.